Now, how about MnO4 2 minus? This one. Will it undergo disproportionation? Yes or no? Before we answer that, let us first look at the reduction potential of MnO4 2 minus to MnO2. So using the Latimer diagrams, you can actually have an interrelation between a substance that is not adjacent to it. So an example would be the MnO4 2 minus to MnO2 conversion. And how do we calculate the standard reduction potential for that transformation? Do you simply add plus 0.27 and 4.27? We do not simply add the standard reduction potentials because the standard reduction potentials are not path-independent state functions. However, we can use the delta G. These delta G values are path-independent functions. So if we convert the standard reduction potential E naught, this E naught values to delta G, and then using Hess law, we can calculate for the total Gibbs free energy needed to convert MnO4 2 minus to MnO2. If we get the delta G values, the Gibbs free energy for the reduction reactions, so you have MnO4 2 minus to MnO4 3 minus, that is plus 0.27. You plug that into your equation where n is equal to 1 because you have one electron here involved in the transformation, and that will give you a delta G value equal to negative 26 kilojoules per mole. You do the same thing for MnO4 3 minus to MnO2. So this plus 0.427 standard reduction potential will give you a standard Gibbs free energy of negative 411.99 kilojoules per mole. If you want to get the delta G for the transformation of MnO4 2 minus to MnO2, you just simply get the sum of the delta G value. So that's negative 26.05095 kilojoules per mole plus negative 411.99095 kilojoules per mole. So this should give you a delta G MnO4 2 minus to MnO2 conversion equal to negative 438.0419 kilojoules per mole. So if you want to get the standard reduction potential for the conversion of MnO4 2 minus to MnO2, all you have to do is to revert it back to the cell potential by using the formula delta G equals negative NFE cell. So you plug in that negative 438 kilojoules per mole as your standard Gibbs free energy, and the N here should be equal to the number of electrons involved. Since the conversion is from MnO4 2 minus to MnO2, you have a total of 2 electrons here. So we plug everything to our equation. We have negative 438.0419 kilojoules per mole equals negative 2 times 96485 coulomb per mole times your standard cell potential for the overall reduction. So this should give you an E value equal to plus 2.27 volts. Alternatively, what you can do is to use the Latimer diagram. So you have your MnO4 2 minus is 0.27, then MnO4 3 minus, and then you have 4.27 volts giving you MnO2. If you want to get the cell potential or the reduction potential from MnO42 minus to MnO2. We can use the same strategy, but instead of calculating delta G, we just cancel everything out from the NFE equation. So to illustrate that, we have negative NFE for the MnO4 2 minus to MnO2 conversion. This is just your delta G value equal to negative NFE cell for your MnO4 2 minus to MnO3 or MnO4 3 minus conversion minus NFE cell for your MnO4 3 minus to MnO2 conversion. So this is delta G as well. And then this whole term here is also delta G. So in essence, we're just adding the delta G's just like what we did previously. So you have your N values as the number of electrons involved. So this one is 2. And then your F will cancel out, same with your negative sign. So you have 2 times E of your MnO4 2 minus 2 MnO2. And this is equal to 1, since 1 electron is involved for MnO4 2 minus to MnO4 3 minus conversion, times E MnO4 2 minus to MnO4 3 minus plus 1 times E MnO4 3 minus to MnO2. So this should give you the E value for your MnO4 2 minus to MnO2 conversion being equal to 1 times plus 0.27 volt plus 1 times plus 4.27 volts over 2. So your E naught MnO4 2 minus to MnO2 should also be equal to plus 2.27 volts. So going back to the question, will MnO4 2 minus disproportionate under acidic conditions? So if we look at what we have solved earlier, the conversion of MnO4 2 minus to MnO2 gives us a standard reduction potential equivalent to plus 2.27 volts. Now, if we rewrite this Latimer diagram into something like this, wherein you have MnO4 minus, that's plus 0.56, and then MnO4 2 minus, and then skipping MnO4 3 minus, and then going directly to MnO2, we can simply write plus 2.27 volts here. And based on our previous discussion, you see that the standard reduction potential is greater for the right side than the left side for MnO4 2 minus. Therefore, it will undergo this proportionation reaction under acidic conditions.